Principles of Economics, a Graphical Approach. This edition follows the standard first-year sequence taught in economics departments everywhere, from scarcity through to market failure. Where a printed textbook can only show a flat diagram, this one lets the diagram respond, rotate a production surface, drag a point along a budget line, move a slider, and watch a market clear at a new price. The economics is the same economics you'd find in any standard course. The way you get to see it is not interactive 3D figures, rotate and inspect, not just view. Hands-on tutorials with real parameters you control. Fully self-contained, works offline, no installation, no account. Free to read, in full, from the first page. Chapter 1, What is Economics? Learning Objectives. Define scarcity and explain why it is the starting point of all economic reasoning. Explain opportunity cost and calculate it in simple numerical examples. Read a production possibilities frontier and explain why it is typically bowed outward. Distinguish positive economic statements from normative ones. 1. Scarcity and the economic problem. Economics begins with a single, unavoidable fact: human wants are effectively unlimited, and the resources available to satisfy them are not. Time, labor, land, capital equipment, and raw materials are all finite at any given moment, while the list of things people would like to have, more goods, more services, more leisure, has no natural stopping point. This mismatch between limitless wants and limited resources is called scarcity, and it is the condition that makes economics necessary as a discipline in the first place. If resources were unlimited, there would be no need to choose between competing uses for them, and most of the questions economics asks would simply not arise. Because resources are scarce, every individual, firm, and society is constantly forced to choose. A student choosing how to spend an evening, a firm choosing how many workers to hire, and a government choosing how to allocate a budget are all facing the same underlying problem in different guises. Given limited means, what should be done with them? Economics is best understood not as the study of money, but as the study of how individuals and societies make these choices, and what the consequences of those choices turn out to be. 2. Opportunity cost. Because choosing to use a resource one way means it cannot simultaneously be used another way, every choice carries a cost beyond any money changing hands. The opportunity cost of a decision is the value of the next best alternative that had to be given up to make it. A student who spends 3 hours studying for an economics exam has, as the opportunity cost of that choice, whatever else those 3 hours would otherwise have been worth to them, perhaps 3 hours of paid work, or 3 hours of leisure. Opportunity cost is the concept that separates economic reasoning from simple accounting. An accountant looking at a decision to attend university, for instance, might tally tuition, textbooks, and accommodation as the cost. An economist adds to that list the income the student could have earned had they worked instead. The foregone wages are a real cost of the decision, even though no invoice is ever issued for them. Nearly every result in the chapters that follow rests on this idea, that the true cost of anything is what must be sacrificed to obtain it, not merely what is paid for it in money. Drag either point along the curve to see opportunity cost as a slope, the ratio of y given up to x gained between any 2 points. This curve illustrates the slope concept only. The full production possibilities frontier, including what makes points on it efficient and points beyond it unattainable, is developed properly in Chapter 11. 3. Positive and normative economics. Economic statements come in 2 distinct kinds, and confusing them is one of the most common sources of muddled reasoning in the subject. A positive statement is a claim about what is, was, or will be. It describes or predicts, and in principle it can be checked against evidence. Raising the minimum wage to $25 an hour will reduce total hours worked in the fast food sector is a positive statement. Economists may disagree sharply about whether it is true, and by how much, but it is the kind of claim that data can in principle settle. A normative statement is a claim about what ought to be. It expresses a value judgment, not a testable prediction. The minimum wage should be raised to $25 an hour is a normative statement. No amount of data can, by itself, prove it right or wrong, because it depends on what the speaker values, not only on what the facts are. Much of the analytical machinery in this book, production functions, cost curves, indifference maps, is built to answer positive questions. What will happen if a price changes, a tax is imposed, or a firm's technology improves? What society should then do with that information is a separate, normative question, and this book will try to be explicit about which kind of claim is on the table at any given point. Chapter Summary. Scarcity, unlimited wants against limited resources, is the starting condition that makes economic choice necessary. Opportunity cost is the value of the next best alternative given up by a choice. It is the true cost of any decision, not merely its money price. Positive statements describe or predict and can in principle be tested against evidence. Normative statements express value judgments and cannot. Review questions. Explain, using your own daily schedule as an example, what the opportunity cost of reading this chapter was for you. Classify each of the following as positive or normative. A. Unemployment fell to 4% last quarter. B. The central bank should prioritize employment over inflation. C. A carbon tax will reduce emissions by roughly 8%. Chapter 5 will apply a very similar bowed frontier logic, resources that are not equally productive in every use, to a single firm's isequants. Chapter 11 will show the same logic applied to a whole economy's production possibilities frontier. Keep this pattern in mind as you meet it again in both places. Chapter 2, Supply and Demand. Learning Objectives. Explain what a demand curve and a supply curve represent, and list the main factors that shift each one. Distinguish a shift of a curve from a movement along it. Find a market's equilibrium price and quantity, and explain what consumer and producer surplus measure there. Explain why a price ceiling or price floors set away from equilibrium creates a shortage or a surplus. The market in miniature, supply, demand, and the price that reconciles them. Drag the yellow line away from equilibrium, and watch a surplus or a shortage appear. The rest of this chapter works out exactly where each curve comes from, and exactly what happens when that price is held away from where it wants to settle. 2.1 Demand, Determinants and the Demand Curve. The demand curve for a good shows the quantity buyers are willing and able to purchase at each possible price, holding everything else about the market fixed. It slopes downward. As price falls, buyers are willing to buy more, both because existing buyers purchase larger quantities, and because lower prices draw in new buyers who were unwilling to pay more. This inverse relationship between price and quantity demanded is often called the law of demand. Price is only one influence on how much of a good people want to buy. A change in any of the following shifts the entire demand curve. Every point on it moves, not just one. Income. For most goods, higher income increases demand. These are called normal goods, though for a smaller class of inferior goods higher income actually decreases demand. The price of related goods, a rise in the price of a substitute increases demand for this good, while a rise in the price of a complement decreases it. Tastes and preferences, expectations about future prices or income, and the number of buyers in the market. It is worth fixing this distinction early, since it returns in section 2. 4. A change in the good's own price moves the buyer along a fixed demand curve, while a change in any of these other factors moves the whole curve. The demand curve isn't assumed, it falls out of a consumer maximizing utility subject to a budget constraint. Each tangency above is one price-quantity pair. the collection of tangencies, projected into price quantity space, is the individual demand curve. Section 2.3's Figure 2. 3 then uses a straight line version of this curve for the market diagram, since a straight line has a finite maximum price, and therefore a calculable consumer surplus, a simplification worth remembering, not forgetting. 2. Supply, determinants, and the supply curve. The supply curve shows the quantity sellers are willing and able to offer at each possible price, holding everything else fixed. It slopes upward. A higher price makes it worthwhile for firms to produce and sell more, both because existing firms expand output, often at rising marginal cost, as Chapter 5 derives in detail, and because higher prices draw in new sellers for whom production was not previously worthwhile. As with demand, several factors shift the entire supply curve rather than moving a seller along it. Input prices, cheaper labor, capital, or materials let firms supply more at every price. Technology, a production improvement lowers cost and shifts supply outward, exactly the kind of change Chapter 5's cost curves are built to describe, expectations about future prices, and the number of sellers in the market. A change in the goods' own price is, once again, a movement along the existing supply curve, not a shift of it. The supply curve isn't asserted either, it falls out of a cost-minimizing firm's expansion path, projected into cost-quantity space. The isoquant map above uses Cobb-Douglas production standard throughout this book. The cost curves use representative numbers chosen to produce the U-shape most textbooks draw, since a genuine long-run U-shape needs either a fixed short-run factor, section 5, or a richer technology than Cobb-Douglas admits, a simplification worth remembering, not forgetting. Section 2.3's Figure 2.3 then uses a straight-line version of this curve for the market diagram, for the same reason Section 2.1 flagged for demand. 2.3 Market equilibrium. Put the demand curve and the supply curve on the same axis, and they cross exactly once, at the price where the quantity buyers want to purchase equals the quantity sellers want to sell. This is the market's equilibrium, the only price at which there is neither a surplus, sellers wanting to sell more than buyers want to buy, nor a shortage, buyers wanting to buy more than sellers want to sell. At any other price, the imbalance itself creates pressure that pushes price back toward equilibrium. A surplus pushes price down as unsold sellers compete for buyers, a shortage pushes price up as buyers compete for scarce goods. The gap between what buyers were willing to pay and what they actually pay is consumer surplus. The gap between what sellers actually receive and the minimum they were willing to accept is producer surplus. Together they measure the total gains from the market existing at all, everything buyers and sellers get from trading with each other rather than not trading. The red region is consumer surplus. For every unit up to the equilibrium quantity, it is the gap between the height of the demand curve, what that unit was worth to some buyer, and the price actually paid. The blue region is producer surplus, the gap between the price received and the height of the supply curve, the minimum a seller would have accepted for that unit. Drag the yellow price line away from equilibrium and watch both regions change, and a surplus or shortage open up between the two curves. Total surplus is largest exactly at equilibrium, and shrinks the further price is pushed from it. Both curves here are drawn as straight lines deliberately, the standard textbook convention, because a straight line demand curve has a finite maximum price, where it meets the vertical axis, and therefore a finite, calculable consumer surplus. A curved demand function, derived directly from consumer preferences, does not generally have this property, a detail worth remembering rather than glossing over. 2.4 Shifts versus movements along a curve. One of the most common sources of confusion in this material is conflating two different kinds of change. A movement along a curve happens only because the goods' own price changed, the curve itself stays put, and the buyer or seller simply moves to a different point on it. A shift of a curve happens because something other than the goods' own price changed, income, input costs, technology, the price of a related good, and so on, and the entire curve relocates, so that a new quantity is now associated with every price, including the original one. The two are easy to mix up in speech. Demand went up could describe either a movement, more was bought because price fell, or a shift, more is now bought at every price, because income rose, which is exactly why economists insist on the more awkward but unambiguous phrasing, quantity demanded changes with a movement along the curve. Demand itself changes only with a shift of the curve. Play each panel and watch closely. In the movement panels the curve itself never moves, only the point on it. In the shift panels the whole curve relocates, shown against its faded original position, while the fixed reference quantity ends up at a new price. 2.5 Price ceilings and price floors. A price ceiling is a legal maximum price, set below equilibrium to keep a good affordable. Rent control is the standard example. Because the ceiling sits below the price that would otherwise clear the market, quantity demanded at that price exceeds quantity supplied, a shortage. The price cannot rise to close the gap, since that is precisely what the ceiling forbids, so the shortage persists, typically resolved instead by queues, waiting lists, or sellers rationing by some means other than price. A price floor is a legal minimum price, set above equilibrium. The minimum wage is the standard example, treating labor as the good being bought and sold. Because the floor sits above the market clearing price, quantity supplied exceeds quantity demanded at that price, a surplus. For a minimum wage, that surplus takes the form of workers willing to work at the floor wage who cannot find employment at it. Both cases share the same underlying logic. Any price held away from equilibrium by law, rather than by the market's own adjustment, leaves an imbalance that the price itself is no longer free to correct. Press animate ceiling or animate floor to watch the price move away from equilibrium, or grab the white line yourself. Notice the yellow triangle. It is surplus that existed at equilibrium, and simply vanishes once price is held away from it, not transferred to buyers, not transferred to sellers, just gone. That triangle is deadweight loss, and it grows the harder the price is pushed away from where the market would have settled on its own. It is tempting to read a price ceiling as simply helping buyers, and a price floor as simply helping sellers, but the red and blue regions in the figure tell a more specific story. A price ceiling redistributes surplus from sellers to the buyers who still manage to purchase the good. Those buyers now pay less than they would have at equilibrium, at sellers' direct expense. But not every buyer who wanted the good at the equilibrium price gets to be one of them, because quantity traded falls to whatever the shortage-constrained sellers are willing to supply. Some willing buyers are simply rationed out, typically by queues or waiting lists rather than by price. The ceiling helps the buyers who get served, and does nothing at all for the buyers who do not. A distinction that helps buyers said as a blanket claim, quietly erases. A price floor works the same way in reverse. Using the minimum wage framing, workers who keep their jobs at the floor wage are genuinely better off. They earn more per hour than the equilibrium wage would have paid, a transfer from employers to them directly. But because employers respond to the higher wage by demanding less labor, quantity traded falls, and some workers who would have been employed at the equilibrium wage are not employed at all. The floor helps the workers who keep their jobs, and does nothing for the workers who lose them or never find one. Again, a real distinction inside the group the policy is meant to help. The deadweight loss triangle is a third thing again, separate from either transfer. It is not sellers' loss becoming buyers' gain, or employers' loss becoming workers' gain. It is the surplus that belonged to trades which no longer happen at all. The buyers and sellers, or workers and employers, who would have happily transacted at the equilibrium price but no longer can under the controlled one. No one receives that surplus, it simply stops existing. Evaluating a price ceiling or floor honestly means weighing a real transfer to some members of the intended group against real losses to other members of that same group, plus a pure loss that helps no one at all, not simply asking whether the policy's stated beneficiaries, as a whole, appear to benefit. 2.6 Tutorial, shift the market yourself. The tool below starts from the same market as figure 2. 3. Use the sliders to apply a demand shock, income, tastes, the price of a related good, or a supply shock, input costs, technology, and watch the whole curve, and the equilibrium, relocate. The original equilibrium stays marked in gray so you can see exactly how far, and in which direction, the market has moved. Try a positive demand shock on its own first, notice both equilibrium price and quantity rise. Then try a positive supply shock on its own, quantity rises again, but price falls this time. Finally, try moving both sliders together in the same direction and see if you can predict, before looking at the numbers, whether the equilibrium quantity change will be larger or smaller than either shock produced alone. Chapter Summary. The demand curve slopes downward and shifts with income, the price of related goods, tastes, expectations, and the number of buyers. The supply curve slopes upward and shifts with input prices, technology, expectations, and the number of sellers. A change in the good's own price causes a movement along a curve, a change in anything else causes the curve itself to shift. Market equilibrium is the price at which quantity demanded equals quantity supplied. Consumer and producer surplus together measure the gains from trade at that price. A price ceiling below equilibrium causes a shortage, a price floor above equilibrium causes a surplus, because the price is no longer free to adjust and clear the market. Review questions. A rise in the price of coffee is followed by an increase in the price of tea. Is this a movement along tea's demand curve, or a shift of it? Explain which determinant of demand is responsible. A new production technology lowers the cost of manufacturing solar panels. Draw, in words, what happens to the supply curve for solar panels, and explain what happens to the equilibrium price and quantity as a result. Using figure 2. 3S logic, explain why a price above equilibrium, even one nobody is legally forcing, tends not to persist in an ordinary competitive market. A city imposes a price ceiling on rental apartments, set below the market equilibrium rent. Explain, step by step, why this produces a shortage of apartments rather than simply cheaper rent for everyone who wants one. A minimum wage is set above the equilibrium wage in a competitive labor market. Identify 3 distinct groups affected: workers who keep their jobs, workers who lose or never find employment, and employers, and explain what happens to each group's welfare. Then explain why the deadweight loss triangle belongs to none of the 3. Using figure 2. 6. Apply a demand shock of +3 and a supply shock of -2 at the same time. Predict, before checking, whether the equilibrium price will rise or fall, then verify. Chapter 3, Elasticity. Learning objectives. Define price elasticity of demand, and classify a good as elastic, inelastic, or unit elastic. List the main factors that make demand for a good more or less elastic. Explain, and show graphically, why the relationship between price and total revenue depends entirely on elasticity. Define price elasticity of supply, income elasticity, and cross-price elasticity, and interpret their signs. 3.1 Price elasticity of demand. Chapter 2 established that demand curves slope downward, but it said nothing about how much quantity demanded responds to a given price change, and that turns out to matter enormously for real decisions, from how a firm should price a product to how much revenue a tax on a good will actually raise. Price elasticity of demand measures exactly this responsiveness, the percentage change in quantity demanded divided by the percentage change in price that caused it. Because demand curves slope downward, this ratio is technically negative. Price and quantity move in opposite directions, but economists conventionally report its absolute value and speak of it as a positive number. When that number exceeds 1, demand is elastic, quantity demanded changes proportionally more than price did. When it is less than 1, demand is inelastic, quantity demanded changes proportionally less than price did. When it equals exactly 1, demand is unit elastic. 2 Determinants of elasticity. Several features of a good make its demand more or less elastic. The availability of substitutes matters most. The easier it is to switch to something else, the more elastic demand becomes, since a small price rise sends buyers elsewhere. Whether a good is a necessity or a luxury matters too. Necessities tend toward inelastic demand, since buyers keep purchasing them even as price rises, while luxuries tend toward elastic demand. The time horizon matters. Demand for most goods becomes more elastic over longer periods, because buyers eventually find substitutes, change habits, or adjust their equipment options that are not available the moment a price changes. Finally, the share of the budget a good commands matters. A price rise in something that costs very little of a buyer's total spending barely changes their overall budget, so demand for cheap goods tends to be more inelastic than demand for expensive ones. 3 Elasticity and total revenue. Total revenue is simply price multiplied by quantity, the total amount buyers spend and sellers receive. What elasticity determines is which direction total revenue moves when price changes. If demand is elastic, a price increase causes quantity demanded to fall by a larger percentage than price rose, so total revenue falls. If demand is inelastic, a price increase causes quantity demanded to fall by a smaller percentage than price rose, so total revenue rises. Exactly at the unit elastic point, total revenue is neither rising nor falling, it is at its maximum. This is the same demand curve from figure 2.3 in the previous chapter. Even a perfectly straight-line demand curve is not equally elastic everywhere along its length. The orange upper segment, where price is high and quantity is low, is elastic. The blue lower segment, where price is low and quantity is high, is inelastic, and the two meet at exactly one unit elastic point. The bottom panel plots total revenue at every quantity along the same curve. It rises through the elastic region, peaks precisely at the unit elastic point, and falls through the inelastic region, because that is, by definition, what elastic and inelastic mean for revenue. 3 Price elasticity of supply. Price elasticity of supply is defined the same way, applied to sellers instead of buyers, the percentage change in quantity supplied divided by the percentage change in price. Supply tends to be more elastic when firms can expand production easily and quickly, when they hold spare capacity, can add workers or shifts without much extra cost, or can shift resources in from other uses, and more inelastic when production is capacity constrained or resources are specialized and hard to reallocate. As with demand, elasticity of supply generally rises over longer time horizons, since firms can build new capacity given enough time, even when they cannot in the short run. 3 Income and cross-price elasticity. Price is not the only variable elasticity can be measured against. Income elasticity of demand is the percentage change in quantity demanded divided by the percentage change in income. Its sign, not just its size, carries the information. A positive income elasticity means the good is normal, buyers purchase more of it as income rises, while a negative income elasticity means the good is inferior, buyers purchase less of it as income rises, typically because they switch to a preferred, pricier alternative once they can afford to. Cross-price elasticity of demand is the percentage change in quantity demanded of one good divided by the percentage change in the price of a different good. Here too the sign carries the meaning. A positive cross-price elasticity identifies substitutes. A price rise in one good pushes buyers toward the other, raising demand for it, while a negative cross-price elasticity identifies complements. A price rise in one good, such as printers, reduces demand for the other, such as ink, because the two are typically bought and used together. 3.6 Tutorial, explore elasticity yourself. Drag the point along the same demand curve from figure 3.1 and watch elasticity, and its consequences for revenue, update in real time. Start near the top of the curve, where quantity is low, and drag slowly downward. Watch for the exact instant the status line switches from elastic to inelastic, that is the unit elastic point, and it should be the same point figure 3. 1 already marked. Notice, too, that the advice about raising or lowering price flips exactly at that same point. On one side, a price increase helps revenue, on the other, it hurts it. Chapter Summary. Price elasticity of demand is the percentage change in quantity demanded divided by the percentage change in price. Demand is elastic if this exceeds 1, inelastic if it is below 1, and unit elastic if it equals 1. Elasticity is higher when substitutes are available, for luxuries more than necessities, over longer time horizons, and for goods that command a larger share of the budget. A price increase raises total revenue when demand is inelastic and lowers it when demand is elastic. Total revenue is maximized exactly at the unit elastic point. Price elasticity of supply measures how responsive quantity supplied is to price. Income elasticity's sign identifies normal versus inferior goods, and cross-price elasticity's sign identifies substitutes versus complements. Review questions. A 10% price increase causes quantity demanded to fall by 4%. Calculate the price elasticity of demand, and classify the good as elastic or inelastic. Explain why demand for a specific brand of breakfast cereal is likely to be far more elastic than demand for food, as a broad category. A city raises its transit fare, and total revenue falls. What does this reveal about the elasticity of demand for transit rides at the old fare? Classify each of the following by the sign of the relevant elasticity. A. As income rises, purchases of instant noodles fall. B. As the price of butter rises, purchases of margarine rise. C. As the price of video game consoles rises, purchases of video games fall. Using figure 3. 1. Explain in your own words why a straight-line demand curve cannot be described as simply elastic or inelastic without specifying which point on it you mean. Chapter 4, Consumer Choice and Utility. Learning Objectives. Explain what a utility function represents and what it does not, a ranking of bundles, not a measurable quantity of happiness. Read an indifference curve map, and calculate the marginal rate of substitution. Marginal rate of substitution. Find a consumer's utility maximizing bundle using a budget line. State the tangency condition for consumer equilibrium, and explain what it means in plain terms. Distinguish income effects from substitution effects when a price changes. 4.1 Preferences and utility functions. A consumer with a fixed income must decide how to divide it between goods. Economists summarize a consumer's preferences with a utility function that assigns a number to every bundle of two goods. That number is not a measurable quantity of happiness, it is an ordinal ranking device. If one bundle scores higher than another, the only information conveyed is that the consumer prefers it. The size of the gap between the two scores carries no meaning of its own. As in the previous chapter, the Cobb-Douglas form is a convenient teaching example. The exact functional form is shown below. With the two exponents set equal, it reduces to the square root of x times y. This function rises whenever either good increases, holding the other fixed, and falls to 0 if either good is entirely absent, capturing the ordinary intuition that variety itself has value. 4.2 Indifference curves, and the marginal rate of substitution. An indifference curve plots every bundle of x and y that delivers the same utility level. The consumer is, by construction, indifferent between any two bundles on the same curve. Bundles on a higher indifference curve are strictly preferred to bundles on a lower one, since utility functions are constructed to be increasing in both goods. The slope of an indifference curve at a point is the marginal rate of substitution. Marginal rate of substitution, the rate at which the consumer is willing to trade one good for the other while holding utility constant. It equals the ratio of the marginal utility of X to the marginal utility of Y, shown below. For well-behaved preferences, and Cobb-Douglas preferences are the standard example, indifference curves are smooth, convex curves that never touch either axis, reflecting a preference for variety. A consumer with only good X and none of good Y is always willing to give up quite a lot of X to obtain a little Y. 4.3 The budget line and consumer choice. An indifference curve tells us which bundles the consumer values equally. It says nothing about which bundles the consumer can actually afford. For that we need the price of each good and the consumer's income. A consumer who spends the entire income on the two goods sits on the budget line shown below, every bundle that exhausts exactly the available income. A utility-maximizing consumer chooses the point on the budget line that reaches the highest possible indifference curve. Because indifference curves are convex and the budget line is straight, that point occurs where the budget line is tangent to an indifference curve, where the slope of the indifference curve, the marginal rate of substitution, equals the slope of the budget line, the price ratio. This tangency condition, shown below, is the central result of this section, and it has exactly the same logical shape as the cost minimization condition from Chapter 5. A utility-maximizing consumer allocates spending so that the last dollars spent on X buys exactly as much extra satisfaction as the last dollars spent on Y. The figure shows the utility surface rising toward the back right corner as consumption of both goods increases. The blue contours are indifference curves, slices of the surface at constant utility. The red plane is the budget line for an income of 8, tilted according to the relative price of the two goods. The yellow point marks the utility-maximizing bundle, where the budget plane just touches the highest indifference curve it can reach. This is the same tangency logic as Figure 5. 1. In the following chapter, a cost-minimizing firm and a utility-maximizing consumer are solving structurally identical problems, just with different names attached to the axes. 4. Income and substitution effects. When the price of a good changes, the consumer's optimal bundle changes for two conceptually distinct reasons. The substitution effect is the change in the consumption bundle that would occur if the consumer's purchasing power were held constant. It captures the pure effect of one good becoming relatively cheaper or more expensive than the other, sliding the consumer along a single indifference curve to a new tangency point. The income effect is the change that occurs because a price change also alters how much total utility the consumer's income can buy. A fall in the price of X, for instance, effectively makes the consumer richer, shifting them onto a higher indifference curve entirely. For an ordinary good, both effects push consumption of a good whose price fell in the same direction, up. For an inferior good, the two effects push in opposite directions, though the income effect is not strong enough to reverse the total change. Section 4. 6 takes up the extreme case, the rare given good, where the income effect dominates entirely, once the decomposition tools needed to analyze it are in place. Suppose the two prices are equal, and income is 8. The tangency condition reduces, for this utility function, to the rule that the consumer always buys equal quantities of X and Y whenever the two prices are equal. Splitting the budget evenly gives 2 units of each good, and a utility score of 2. If income doubles to 16 with prices unchanged, the same logic gives 4 units of each good and a utility score of 4. Utility doubles when income doubles, the consumer theory mirror image of the constant returns result found for the firm in Chapter 5. 4.5 The Slutsky and Hicks decomposition. Section 4. 4 split a price change into a substitution effect and an income effect, but glossed over a real question: what exactly does holding purchasing power constant mean? There are 2 different, both perfectly rigorous, answers, and they give slightly different substitution effects. The Slutsky decomposition compensates the consumer with just enough extra income to afford their original bundle at the new prices. Geometrically, this draws a new budget line with a new price ratio's slope, passing directly through the original optimal point. The Hicks decomposition compensates instead with just enough income to reach the original indifference curve at the new prices, a budget line with the same new slope, but tangent to the old indifference curve rather than passing through itself. The two are not the same amount of compensation. Being able to afford the exact old bundle at new prices also means being able to afford something the consumer would now prefer even more, since one good just got relatively cheaper. A different combination on that same budget line reaches higher utility than sticking with the original bundle. Slutsky compensation is therefore always at least as generous as Hicks compensation for a normal good, and the Slutsky-derived substitution effect is correspondingly at least as large as the Hicks-derived one. Toggle between the two compensation methods. Slutsky's yellow budget line always passes through Hicks's is always tangent to the original indifference curve instead. Watch where point B lands on each. Under Slutsky it sits just above the original indifference curve, since affording the old bundle affords something better too. Under Hicks it sits exactly on it, by construction. Economists generally treat the Hicks version as the theoretically cleaner definition, a substitution effect that holds actual satisfaction fixed, not just the ability to buy a specific bundle. But Slutsky compensation is what a real-world policy could actually implement. A government cannot observe a citizen's indifference curves, but it can observe what a household used to buy and calculate what it would cost at new prices. This is precisely why cost of living adjustments to wages, pensions, and benefits are Slutsky style in practice, even though Hicks compensation is what most theoretical welfare analysis actually uses. 4.6 The Giffen Good. Section 4. 5. Split a price change into a substitution effect and an income effect using two different, equally rigorous, compensation methods. In the rare Giffen good case, the income effect is large enough and perverse enough to dominate the substitution effect entirely, so that a lower price actually reduces the quantity demanded. This is genuinely difficult to produce from well-behaved preferences. The Cobb-Douglas utility used throughout this book, for instance, can never generate it, since its income and substitution effects always move together by construction. What follows applies the decomposition just established to show the logic of the result, not a formula that happens to produce Giffen behavior, but a geometric decomposition of exactly what would have to be true for it to occur. The silent default shows the settled outcome directly, point C, with less X than at A despite the lower price. Press play with narration to walk through how it got there, the original optimum, the price fall, the substitution effect alone, AB, and the income effect that overwhelms it, BC, and, as a closing beat, the same income vs substitution logic applied to labor supply, producing a backward-bending supply curve. That reversal is the entire definition of a Giffen good, and it requires an unusually large, negative income effect, historically, deeply inferior staple goods eaten mainly by the very poor, where a price fall frees up so much of a tight budget that the consumer switches away from the staple toward something they actually prefer. Chapter Summary. A utility function, U, X, Y, is an ordinal ranking of consumption bundles, not a measurable quantity. Indifference curves show all bundles yielding a given utility level. Their slope is the marginal rate of substitution, the ratio of the marginal utility of X to the marginal utility of Y. The budget line shows all bundles costing exactly the consumer's income. Its slope is the negative of the price ratio between the two goods. Utility maximization occurs where the marginal rate of substitution equals the price ratio, the tangency of an indifference curve, and the budget line. A price change can be decomposed into a substitution effect, movement along an indifference curve, and an income effect, movement to a different indifference curve. Slutsky compensation affords the original bundle at new prices. Hicks compensation affords the original utility level. They are not the same amount. Slutsky is always at least as generous, so its substitution effect is at least as large. Hicks is the theoretically cleaner definition. Slutsky is what real cost of living adjustments actually use, since it only requires observing what a household bought, not their indifference curves. This chapter's tangency condition and chapter 5's cost minimization condition are the same mathematical structure applied to two different decision makers. Review questions. Explain why the specific numbers a utility function assigns to bundles carry no meaning on their own. A consumer's utility function is the square root of x times the square root of y, Cobb-Douglas with equal weights. If the price of x is $1 and the price of y is $4, what is the consumer's optimal ratio of y to x? Why must indifference curves be convex to the origin for the tangency condition to identify a utility maximum rather than a minimum? Describe, in words, the difference between an inferior good and a given good. A consumer's income is compensated after a price fall using the Slutsky method rather than the Hicks method. Explain why the Slutsky compensated bundle ends up on a slightly higher indifference curve than the original one, while the Hicks compensated bundle does not. Compare the tangency condition in this chapter to the cost minimization condition in chapter 5. What economic decision maker plays the role of the firm in each case, and what plays the role of the price ratio? Chapter 5, Production and Costs. Learning objectives. Explain what a production function describes and why it summarizes a technology, not a firm's choices. Read an isoquant map and calculate the marginal rate of technical substitution, marginal rate of technical substitution. Find a firm's cost-minimizing input combination using isocost lines. Trace the expansion path and explain what it means for a firm's long-run scale decisions. Distinguish short-run from long-run cost curves and describe the standard shapes economists draw for them. 5.1 The production function. A firm turns inputs into output. Economists summarize this process with a production function, a purely technological relationship between input quantities and the output they can produce. It says nothing about prices, costs, or profit. It answers one question only: given a certain amount of labor and capital, how much output can the firm physically produce? One of the most widely used production functions in introductory economics is the Cobb-Douglas form, shown below, where is a number between 0 and 1 that describes labor's relative contribution to output. With the two exponents equal, it reduces to the square root of labor times capital, a convenient case in which labor and capital contribute symmetrically. This function has two properties worth noticing immediately. First, output rises whenever either input rises, holding the other fixed. More of either input, on its own, produces more output. Second, output is 0 whenever either input is 0. A factory with machines and no workers produces nothing, and a workforce with no equipment produces nothing. 5.2 Isoquants and the marginal rate of technical substitution. Because the same output level can usually be produced with many different combinations of labor and capital, it is useful to plot all the combinations that yield a given quantity of output. This curve is called an isoquant, equal quantity. A firm sitting anywhere along a single isoquant is producing exactly the same output, just using a different mix of inputs, more labor and less capital, or the reverse. The slope of an isoquant at any point is the marginal rate of technical substitution. Marginal rate of technical substitution, the rate at which the firm can give up one input and replace it with the other while holding output constant. It equals the ratio of the marginal product of labor to the marginal product of capital, shown below. For the Cobb-Douglas function, isoquants are smooth, convex curves that never touch either axis, reflecting the fact that output collapses to 0 if either input is driven to 0. 5.3 Isocost lines and cost minimization. An isoquant tells the firm what combinations of L and K are technically capable of producing a given output. It does not tell the firm which of those combinations is cheapest. For that, we need input prices. Let W be the wage rate, the price of labor, and R be the rental rate of capital. Rearranging the firm's total input cost gives the isocost line shown below, a straight line showing every combination of L and K that costs exactly C to employ. A cost-minimizing firm chooses the point on the target isoquant that touches the lowest possible isocost line. Because isocost lines are straight and isoquants are convex, that point is where the isoquant is tangent to an isocost line, where the slope of the isoquant, the marginal rate of technical substitution, equals the slope of the isocost line, the input price ratio. This tangency condition, shown below, is the central result of this section. A firm minimizes cost by hiring inputs up to the point where the last dollars spent on labor buys exactly as much extra output as the last dollars spent on capital. The figure shows the production surface rising toward the back right corner as both labor and capital increase. The blue contour lines are isoquants, slices of the surface at constant output. The four colored planes are isocost lines for budgets of 2, 4, 6, and 8, each tilted according to the input price ratio. The dot on each plane marks where that budget's isocost line just touches the highest isoquant it can reach, the cost-minimizing bundle for that budget, and the yellow dashed line connecting the four dots is the expansion path, covered properly in the next section. Drag to rotate, scroll to zoom, or use the button to switch to the flat isoquant map a textbook would normally print on the page. 5 for the expansion path. Now let the firm's budget C rise, from 2, to 4, to 6, to 8, while the wage and rental rate stay fixed. Each budget defines its own isocost line, and each isocost line has its own tangency point with an isoquant. The curve connecting all of these tangency points, as scale expands, is called the expansion path. For a Cobb-Douglas production function, the expansion path is a straight line through the origin. As the firm scales up, it keeps hiring labor and capital in a fixed ratio determined entirely by and the price ratio W/R, regardless of how large output grows. This is a distinctive prediction of Cobb-Douglas technology, not a general law of production. Other production functions can generate expansion paths that bend as scale changes. Suppose the wage and rental rate are both 2. The cost-minimizing condition reduces, for this production function, to the rule that the firm always hires equal quantities of labor and capital at any budget. If the firm has 8 to spend, it splits the budget evenly, 2 units of labor and 2 units of capital, giving an output of 2. Doubling the budget to 16 gives 4 units of each input, and an output of 4. Output doubles when the budget doubles, because this particular production function has constant returns to scale. 5 short-run and long-run cost curves. Everything above assumed the firm is free to choose both L and K, the long run, in which all inputs are variable. In the short run, at least one input, conventionally capital, since machinery and plant take time to install, is fixed at some level K. The firm can still vary labor, but it can no longer move along the expansion path. It is stuck on a single horizontal slice of the production surface at height K. This distinction generates the two families of cost curves that appear throughout the rest of this course. The long-run average cost, long-run average cost, curve traces the lowest possible average cost at each output level, once the firm has had time to adjust every input, including plant size, to its cost-minimizing expansion path combination. The short-run average cost curve, by contrast, shows average cost for a firm that built its plant for one particular output level and must now produce more or less than that with a fixed K. Textbooks conventionally draw short-run average cost curves as U-shaped and tangent to a U-shaped long-run average cost envelope from above at exactly one output level, the level the plant was actually designed for. A note for later chapters, the U-shape conventionally drawn for these curves, and the exact way short-run average cost is said to touch long-run average cost, deserves closer mathematical scrutiny than most introductory treatments give it. That scrutiny is deferred to a later chapter, once the standard apparatus in this chapter is fully in hand. Drag along either panel to move the short run plant size. Toggle long run /short run /both, and ray and tangent to see average and marginal cost traced out the same way figure 2. To derive them, the slope of a ray from the origin is average cost, the slope of the tangent is marginal cost. Same cost numbers as figure 2. 2 throughout, so the minimum here, an output of 6 at a price of 2.4, is the same point that figure derived the supply curve from. 5.6 Tutorial, minimize cost yourself. The tangency condition in section 5. 3 is easiest to internalize by breaking it, on purpose, and then fixing it. The tool below gives you a fixed budget and lets you place the firm's labor capital bundle anywhere along the isocost line for that budget. Most points you can pick are wasteful, they spend the whole budget but land on a lower isoquant than the budget allows. Only one point on each isocost line reaches the highest isoquant available, the cost-minimizing bundle from section 5. 3. Try 3 things. First, with W and R left equal, drag the point until the status readout confirms you have found the cost-minimizing bundle, and check that it lands where labor and capital are equal, matching the tangency condition from section 5. 3. Second, raise W relative to R and find the new optimum. Labor has become relatively more expensive, so the cost-minimizing bundle should now use less of it. Third, raise the budget C with W and R held fixed, and confirm the optimal L and K both scale up in the same fixed ratio. This is the expansion path from section 5. 4. Traced out one budget increase at a time. Chapter Summary. A production function describes the maximum output obtainable from given input quantities. It is a technological relationship, independent of prices. Isoquants show all input combinations yielding a given output. Their slope is the marginal rate of technical substitution, the ratio of the marginal product of labor to the marginal product of capital. Isocost lines show all input combinations costing a given total. Their slope is W/R. Cost minimization occurs where the marginal rate of technical substitution equals the input price ratio, the tangency of an isoquant and an isocost line. The expansion path traces cost-minimizing input combinations as the budget and output rises. For Cobb-Douglas production, it is a straight line through the origin. The short run fixes at least one input, the long run allows all inputs to vary. This distinction produces 2 separate families of cost curves, short-run average cost and long-run average cost. Review questions. Explain, in your own words, why a production function contains no information about prices. A firm's output is the square root of L times the square root of K, Cobb-Douglas with equal weights. If the wage is $4 and the rental rate is $1, what is the cost-minimizing ratio of K to L? Why must isoquants be convex to the origin for the tangency condition to identify a cost minimum rather than a cost maximum? Explain why a Cobb-Douglas expansion path is a straight line through the origin, and describe a production technology for which it would not be. A firm built its plant to produce 1,000 units per month at minimum average cost. Explain what happens to its short-run average cost, relative to the industry's long-run average cost, if demand forces it to produce 1,400 units instead. Chapter 6, The Theory of the Firm. Learning Objectives. Define total, average, and marginal revenue, and explain how Mr. relates to R for any downward-sloping demand curve a firm faces. Explain why price-taking in a perfectly competitive market makes an individual firm's demand curve horizontal, so that average revenue, marginal revenue, and price are all equal. Find a competitive firm's profit-maximizing output using the rule that marginal revenue equals marginal cost. Distinguish the shutdown decision from the exit decision, and identify the price at which each becomes relevant. Explain why economic profit is driven to zero in long-run competitive equilibrium, and why that outcome is a consequence of free entry rather than an assumption about individual firms. 6.1 Revenue. Chapters 4 and 5 build the two things a firm needs to know about itself: what it costs to produce a given quantity, and what technology allows it to produce in the first place. Neither says anything about what the firm can sell that output for. This chapter adds the missing piece, revenue, and puts the two sides together to explain how a firm actually decides how much to produce. Total revenue, TR, is price multiplied by quantity. Average revenue, R, is revenue per unit, which is simply price again, whatever the demand curve looks like. Marginal revenue, Mr., is the change in total revenue from selling one more unit. For a firm facing a downward sloping demand curve, these three are related in a specific geometric way. Average revenue is the slope of a wave from the origin to any point on the total revenue curve. Marginal revenue is the slope of the tangent at that point. Because a falling demand curve means the firm must cut price on every unit sold, not just the last one, to sell one more, marginal revenue always lies below average revenue, and falls at exactly twice the rate. This is the same relationship Chapter 3 used to connect elasticity to total revenue. Where marginal revenue is positive, total revenue is rising. The elastic region, where marginal revenue is negative, total revenue is falling. The inelastic region, where marginal revenue is zero, total revenue is at its maximum. Exactly at the unit elastic point. This is the general case: any firm facing a downward sloping demand curve has R falling as the wave from the origin, and Mr falling twice as fast as the tangent. Section 6. 2 shows what happens to this picture once a firm is small enough to take the market price as given. 6.2 Perfect competition, characteristics of a competitive market. A perfectly competitive market has 4 defining features: many buyers and sellers, none large enough to affect the market price by acting alone, a homogeneous product, so buyers have no reason to prefer one seller's output over another's, free entry and exit, so firms can start or stop producing without being blocked by cost or legal barriers, and full information, so buyers know what they are paying and firms know the technology available to them. Few real markets satisfy all 4 exactly, but many: agricultural commodities, foreign exchange, shares of a large company, come close enough that the model's predictions are useful. The consequence that matters most for this chapter follows directly from many small sellers. Because no single firm can influence the market price by changing its own output, each firm is a price taker. It faces a horizontal demand curve at the market price P*, set by the intersection of market supply and market demand, exactly as Chapter 2 described. This is not a different revenue story from Section 6. 1. It is the limiting case of it. As the market level demand curve a firm faces gets flatter and flatter, the gap between average and marginal revenue shrinks toward zero. A perfectly competitive firm faces a demand curve that is perfectly flat, so average revenue, marginal revenue, and price are all equal for every unit it sells. Average revenue, marginal revenue, and price collapse into a single horizontal line. Drag the white price line in the firm panel. The firm always produces where it crosses MC, that's Section 6. 4S rule, not a new one. Watch the shaded band flip from green, profit, P** above ATC, to red, loss, P** below ATC, as you cross ATC's minimum. Right at P* equals 2. 4. The band vanishes, 0 economic profit, the exact long-run outcome. Section 6. 6 derives from free entry and exit. 6.3 The firm's short-run output decision. With average revenue, marginal revenue, and price all equal, a competitive firm's decision simplifies enormously. It does not need to think about how its own output affects the price. That question is settled by the whole market, not by any one firm. What remains is a single choice: given the price the market has set, How much should this firm produce? Profit is total revenue minus total cost. Profit is maximized at the output where the addition to revenue from one more unit exactly equals the addition to cost, where marginal revenue equals marginal cost. Producing less than that quantity leaves profitable units unsold, producing more adds units that cost more than they bring in. Drag the white price line. Above ATC, the green band is economic profit. Below ATC but above AVC, the amber band is a loss the firm accepts anyway. Producing still covers all variable cost and part of fixed cost, better than covering none of it. Drag below the blue shutdown price marker, AVC's minimum, and the firm stops producing entirely, the exact boundary section 6.5 describes. The bold white segment of MC above that point is the firm's short-run supply curve, the same curve Chapter 2 introduced, now shown for where it actually comes from. 6.4 Profit maximization, where marginal revenue equals marginal cost. Because a price-taking firm has marginal revenue equal to price, the general rule produce where marginal revenue equals marginal cost becomes the sharper, more familiar rule, produce where price equals marginal cost. The firm's short-run marginal cost curve, the same short-run marginal cost derived in Chapter 5 from the cubic cost technology, is therefore also the firm's short-run supply curve, for any price above the point where short-run marginal cost crosses short-run average cost. Raise the market price and the firm reads a higher quantity off its own MC curve, lower it and the firm reads off a lower one. Nothing about the firm's own preferences enters this decision, only the cost technology and the price the market has already determined. Whether the firm is actually earning a profit at that quantity is a separate question from whether it is maximizing profit. A firm can maximize profit and still be making a loss if the market price sits below average cost at every output level. Sections 6.5 and 6.6 work out what the firm should do in that situation, in the short run and the long run respectively. 6.5 The shutdown decision. Suppose the market price falls below the minimum of short-run average cost, so the firm cannot earn a profit at any output level in the short run. It does not follow that the firm should stop producing immediately. In the short run, at least one cost, the fixed cost tied to capital already in place, has to be paid whether the firm produces or not. The relevant comparison is not does this cover total cost, but does this cover the costs that production itself adds. As long as price covers average variable cost, the portion of average cost that actually depends on output, producing and selling at a loss is still better than shutting down, because the revenue earned covers the variable costs and contributes something toward the fixed cost that must be paid regardless. Only when price falls below the minimum of average variable cost does producing at all make the loss worse than shutting down would. That minimum point is the firm's shutdown price. Below it, the firm produces nothing in the short run, even though it still incurs its fixed costs and reports a loss either way. This is a short-run decision specifically because it takes the fixed cost and the capital that generates it as already committed. Figure 6.3 shows this decision directly. Drag the price below the blue shutdown marker, and the firm's output drops to 0. The bold segment of MC above that point, the segment actually used to answer how much would this firm supply at this price, is the firm's short-run supply curve, the same object Chapter 2 introduced without yet explaining where it comes from. Figure 5. 2's short-run and long-run cost curves show the same underlying asymmetry from a different angle. Notice how steeply short-run average cost rises as output falls toward 0, reflecting fixed cost spread over an ever smaller quantity. 6.6 Long-run equilibrium and 0 profit. The shutdown decision in Section 6.5 assumed the firm's capital was already in place and could not be changed. The long run relaxes that assumption. With enough time, the firm can adjust every input, and, Crucially, for a perfectly competitive market, new firms can enter if the industry is profitable, and existing firms can exit if it is not. Suppose the market price sits above every existing firm's minimum long-run average cost, so firms are earning positive economic profit. Because entry is free, that profit attracts new firms. As more firms enter, market supply shifts outward, Chapter 2's supply and demand mechanics again, and the market price falls. Entry continues exactly as long as profit remains positive. Symmetrically, if firms are making losses, exit reduces supply, and price rises, and exit continues as long as losses persist. The process only stops when price equals the minimum of long-run average cost, the same point, incidentally, where Chapter 2's Figure 2 first showed the supply curve as long-run marginal cost above that minimum. At that price, marginal revenue equals marginal cost, the profit-maximizing condition from Section 6.4, and price simultaneously equals the minimum of long-run average cost, so economic profit is exactly zero. This is not an assumption bolted onto the model, it is the equilibrium outcome of free entry and exit doing exactly what Section 6.2 already assumed they could do. Zero profit here means zero economic profit. Firms are covering every input's opportunity cost, including a normal return on the owner's own capital and effort. They are doing as well as they could be doing anywhere else, no better, no worse. Press play with narration to watch the process itself, not just its end point, supply shifting outward as firms enter, price falling, the profit band shrinking in step on the firm panel, until it vanishes exactly where figures 2 and 6.2 already said it would. The silent default shows the settled state directly, replay the narration any time to see how it got there. 6.7 Tutorial, run a competitive firm. Drag in the market panel to set today's number of firms, too few and you're earning a profit, too many and you're not even covering variable cost. See your firm's actual short-run decision, then press fast forward and watch the market correct itself, entry if you started with too few firms, exit if you started with too many, always landing on the same long-run outcome regardless of where you began. Chapter Summary. Total revenue is PQ, average revenue is TR/Q, which equals P, marginal revenue is the addition to revenue from one more unit sold. For any downward sloping demand curve, Mr. lies below R and falls at twice the rate, a firm must cut price on every unit, not just the marginal one, to sell more. A price-taking firm in a perfectly competitive market faces a horizontal demand curve, so average revenue, marginal revenue, and price are all equal, the general revenue relationship's limiting case, as the demand curve flattens. Profit is maximized where marginal revenue equals marginal cost. For a price taker this becomes price equals marginal cost, making the firm's short-run marginal cost curve, above the shutdown price, its short-run supply curve. A firm should keep producing in the short run as long as price covers average variable cost, even while making a loss, because production still contributes toward unavoidable fixed costs. Below that price, it shuts down. Free entry and exit push long-run economic profit to zero, price settles at the minimum of long-run average cost, where price, marginal revenue, marginal cost, and minimum long-run average cost are all equal simultaneously. Review questions. Explain why average revenue, marginal revenue, and price are all equal for a perfectly competitive firm, but marginal revenue lies strictly below average revenue for a firm facing a downward sloping demand curve. What is different about the two firms' situations, not just their curves? A competitive firm's short-run marginal cost is given by Chapter 5's cost technology. If the market price is 4, at what quantity does the firm produce? Use the same cost technology numbers as Figure 2.2 and Figure 5.2. A firm is making a loss at its profit-maximizing output. Explain the difference between this firm should shut down and this firm should exit the industry, and why they can have different answers in the short run. Suppose every firm in a competitive industry is identical and currently earning positive economic profit. Describe, step by step, the process that brings that profit back to zero, and explain what would have to be true of the industry for that process not to happen. Zero economic profit in the long run means competitive firms are barely surviving. Explain what is wrong with this statement. Chapter 7, Monopoly. Learning objectives. Identify the main sources of monopoly power, and explain why each one blocks the entry that erodes profit in a competitive market. Explain why a monopolist's marginal revenue lies below its average revenue, and connect this to the general revenue relationship from Chapter 6. Find a monopolist's profit-maximizing price and quantity, and explain why price exceeds marginal cost at that point. Measure the deadweight loss from monopoly, and explain what it represents in terms of foregone mutually beneficial trades. Distinguish first, second, and third degree price discrimination, and explain why a monopolist that can discriminate perfectly eliminates deadweight loss entirely. 7.1 Sources of monopoly power. A monopoly is a market with a single seller, and no close substitutes for its product. What makes a monopoly stable, rather than a temporary position competed away by the entry Chapter 6 described, is a barrier that keeps other firms out. 4 sources recur across real markets. Economies of scale can make a single large firm cheaper per unit than several smaller ones, where average cost keeps falling across the entire relevant range of demand. A single firm naturally ends up supplying the whole market, a case usually called a natural monopoly. Legal barriers, patents, copyrights, exclusive licenses, grant a single firm the sole right to sell a good for some period. Control of a key input gives one firm an advantage no rival can replicate without that same input. And network effects make a good more valuable to each user, as more people use it, which can tip an entire market toward a single provider once it gets far enough ahead. 7.2 Demand and marginal revenue for a monopolist. Chapter 6 introduced total, average, and marginal revenue for a firm facing a downward sloping demand curve, then showed that a perfectly competitive firm is the special case where that demand curve happens to be flat. A monopolist is the opposite extreme, because it is the only seller. The demand curve it faces is the market demand curve from Chapter 2, genuinely downward sloping, with no horizontal special case to fall back on. Figure 6. 1S apparatus therefore applies to a monopolist exactly as originally derived, with nothing simplified away. R is the demand curve itself, Mr lies below it, and Mr falls at twice the rate R does. Selling one more unit requires cutting price on every unit already being sold, not just the marginal one, so marginal revenue is always below price for a monopolist. The gap that vanishes entirely for the price-taking firm of Chapter 6 is, for a monopolist, the whole story. 7.3 Profit maximization under monopoly. The profit-maximizing rule itself does not change. A monopolist still produces where marginal revenue equals marginal cost, exactly as any firm does. What changes is how price is read off afterward. A competitive firm's price is fixed by the market before the firm ever decides on quantity. A monopolist's price is determined by its quantity choice, through the demand curve. The monopolist first finds the quantity where marginal revenue equals marginal cost, then reads the price up to the demand curve at that quantity, not across to the MC curve, the way the competitive price equals marginal cost rule would suggest. Because marginal revenue lies below demand at every quantity, the price a monopolist charges always exceeds marginal cost. This markup is not a matter of the monopolist choosing to be unfair, it is the mechanical consequence of facing a downward sloping demand curve, with no competitive discipline forcing price back down to cost. Drag the yellow quantity line away from Q*. Notice Mr. and MC visibly disagree. The readout tells you which direction increases profit. Only at Q** do they meet exactly. Notice price is always read up to the demand curve, never across to MC. That gap between the red dot and the orange MC curve at Q** is the monopoly markup. Section 7. 3 describes 7. For the welfare cost of monopoly. Because a monopolist restricts output below the level where price equals marginal cost, some mutually beneficial trades never happen. There exist buyers willing to pay more than the marginal cost of producing another unit, but the monopolist will not sell to them, since doing so would require cutting price on inframarginal units already sold at a higher price. The lost surplus from these foregone trades is the deadweight loss of monopoly, a pure loss to society, since it is not captured by the monopolist as extra profit either. It is the same triangle concept that will reappear in Chapter 10 for externalities, and in Chapter 12's discussion of Pareto efficiency. Whenever price is prevented from equaling marginal cost, some available gains from trade go unrealized. Press play with narration to watch the comparison unfold, the competitive benchmark first, then Section 7. 3's marginal revenue equals marginal cost outcome, pulling output back, revealing the deadweight loss triangle in the gap between them. Same underlying idea as Figure 2. 5's price ceiling triangle, a legal price control and a monopolist's market power both prevent price from settling at marginal cost, and the lost trades in between are the same kind of loss either way. 7.5 Price discrimination. A monopolist that must charge every customer the same price leaves money on the table. Some buyers would have paid more than the uniform price, and that difference goes to them as consumer surplus rather than to the firm as revenue. Price discrimination is any practice of charging different prices to different buyers, or different prices for different units, for reasons unrelated to cost. First degree, perfect, price discrimination charges each buyer exactly their maximum willingness to pay for each unit, in principle capturing the entire area under the demand curve as revenue, and eliminating deadweight loss entirely, since every unit up to where demand meets marginal cost gets sold. Second-degree discrimination charges different prices for different quantities, bulk discounts, without needing to identify individual buyers. Third-degree discrimination charges different groups of buyers different prices based on an observable characteristic correlated with willingness to pay, student discounts, off-peak pricing, and is the most common form seen in practice. Press play with narration and watch closely as output expands from QM to QC. Consumer surplus, red, doesn't just disappear, it becomes producer surplus, blue, instead, and the deadweight loss triangle, yellow, from Figure 7. 2 closes entirely because every remaining trade now happens. Total surplus is conserved, only who captures it changes. 7.6 Tutorial, set a monopolist's price. Drag the yellow quantity line anywhere. The reference markers show QM, Figure 7.1's profit maximizing point, and QC, Figure 7.2's efficient benchmark, land exactly on each, and the readout tells you what's special about it. They are never the same quantity, which is the whole content of Section 7. 4 Made explorable rather than just stated. Chapter Summary. Monopoly power persists where a barrier, economies of scale, legal protection, control of a key input, or network effects, blocks the entry that would otherwise compete profit away. A monopolist faces the market demand curve directly, so Chapter 6's general revenue relationship, Mr. Below R, falling twice as fast, applies without simplification. Profit maximization is still where marginal revenue equals marginal cost, but price is read off the demand curve at that quantity, not set equal to marginal cost, so a monopolist's price always exceeds marginal cost. Restricting output below the competitive level creates deadweight loss, mutually beneficial trades between the monopolist and buyers willing to pay above marginal cost go unrealized. Price discrimination lets a monopolist capture some or all of that lost surplus instead of leaving it unrealized. Perfect price discrimination eliminates deadweight loss entirely, though it eliminates consumer surplus along with it. Review questions. Explain why a monopolist's marginal revenue curve lies below its demand curve, using the same reasoning Chapter 6 used for any downward sloping demand firm. A monopolist faces demand described by price falling as quantity rises, an intercept of 20, a slope of 1, and has a constant marginal cost of 4. Find the profit maximizing quantity, the price charged, and the size of the deadweight loss triangle. Explain why the monopolist could just charge a lower price and sell more, so it isn't really restricting output is a misunderstanding of the rule that profit maximizing output occurs where marginal revenue equals marginal cost. Give an example of second-degree price discrimination that is not third-degree, and explain the difference in your own words. Why does perfect price discrimination eliminate deadweight loss even though the monopolist still faces no competition? Chapter 8, Monopolistic Competition and Oligopoly. Learning Objectives. Explain why monopolistic competition combines free entry with each firm facing a downward sloping demand curve, and what that combination implies for long-run price. Describe the excess capacity result and explain why it does not arise in perfect competition. Explain what makes oligopoly different from both perfect competition and monopoly, strategic interdependence between a small number of firms. Use a payoff matrix to find a dominant strategy and a Nash equilibrium, and apply this to a simple pricing game. Explain why cartels are difficult to sustain even when collusion would raise every member's profit. 8.1 Monopolistic Competition, Characteristics. Monopolistic competition sits between the two extremes chapters 6 and 7 already covered. Like perfect competition, it has many sellers and free entry and exit. Unlike perfect competition, the product is differentiated, each firm's version is a little different from its rivals, by brand, location, quality, or features, so each firm faces its own downward sloping demand curve rather than the horizontal one a price taker faces. A firm in monopolistic competition therefore behaves like a small monopolist in the short run, it sets marginal revenue equal to marginal cost, and reads price off its own demand curve, exactly as Chapter 7 described. What distinguishes it from true monopoly is that this position is never protected by a barrier, any profit invites entry from a firm offering yet another close substitute. 8.2 Long-run equilibrium and excess capacity. Entry in monopolistic competition works the same way it did in Chapter 6, as long as existing firms earn positive economic profit, new firms keep entering with their own differentiated variants, and each entrant's product pulls some customers away from existing firms, shifting each incumbent's own demand curve inward. Entry continues until demand curves have shifted in enough that each firm's demand curve is tangent to its average cost curve. Profit falls to zero, exactly as it did under perfect competition. The quantity at which that tangency happens is where monopolistic competition and perfect competition part ways. Under perfect competition, the zero profit price sits at the minimum of average cost, because the firm's demand curve is horizontal, and a horizontal line is tangent to a U-shaped average cost curve only at its minimum. Under monopolistic competition, the firm's demand curve still slopes downward even after all the entry has happened, and a downward sloping line is tangent to a U-shaped average cost curve to the left of its minimum. Each firm therefore produces less than the output that would minimize its average cost, and charges a correspondingly higher price. This gap is called excess capacity. The industry could produce the same total output more cheaply with fewer, larger firms each operating near a minimum efficient scale, the cost of maintaining product variety that consumers evidently value enough to accept the markup. Toggle between the two cases. Both firms are tangent to ATC, zero economic profit either way, but the monopolistically competitive firm sits left of ATC's minimum, at a higher price and smaller scale. The shaded region is the gap, capacity the firm could use to produce more cheaply, but doesn't, because its downward sloping demand never lets it. 8.3 Oligopoly and strategic interdependence. An oligopoly is a market with a small number of sellers, each large enough that its own output or pricing decisions visibly affect its rivals, and each aware that its rivals will respond. This is the feature that separates oligopoly from every market structure covered so far. A competitive firm ignores its rivals because it is too small to matter to them. A monopolist has no rivals to consider. A monopolistically competitive firm has many small rivals, none individually worth reacting to. An oligopolist cannot ignore its rivals. Cutting price to gain customers only works if rivals do not cut their own price in response, and whether they will is precisely what the firm has to predict before acting. Drag the orange MC line, and watch how far it moves before anything else does. Inside the gap, a real change in cost produces no price response at all. This is the textbook explanation for why oligopoly prices tend to be sticky, and it follows directly from rivals reacting differently to a price rise than to a price cut. 8.4 Game Theory and the Prisoner's Dilemma. Game theory gives economists a formal way to analyze decisions where each player's best choice depends on what other players choose. A payoff matrix lists the outcome for every combination of choices available to each player. A dominant strategy is a choice that is best for a player regardless of what the other player does. A Nash equilibrium is a combination of choices where neither player can improve their own outcome by unilaterally changing, given what the other player is doing. Before turning to the classic illustration, it is worth noting that a game's outcome depends on more than the payoffs alone. The rules for combining players' choices into a decision matter just as much. A striking real example, during the Cuban Missile Crisis in October 1962, the Soviet submarine B-59's protocol required unanimous agreement among 3 senior officers before launching a nuclear torpedo at pursuing American warships. 2 of the 3, the captain and the political officer, favored firing. The third, Vasily Arkhipov, did not, and because the rule was unanimity rather than majority, his single dissenting vote was enough to block the launch entirely. Change the decision rule from unanimity to a simple majority, and the outcome of that exact same game, with the exact same 2-to-1 split in preferences, flips completely. The rule a game is played under is not a neutral backdrop to the payoffs, it can be the entire difference in what actually happens, and in this case, in whether the reader of this sentence exists to read it. Set the votes to match the real 1962 incident, to authorize, Arkhipov vetoes, with the rule on unanimity required. Then switch the rule to simple majority without touching a single vote. Same 3 people, same preferences, opposite outcome. That is the whole content of this section in miniature. The rule a game is played under is not a detail, it can be the entire result. The classic illustration is the prisoner's dilemma, applied here to 2 firms choosing between a high price and a low price. If both firms charge the high price, both earn a solid profit. If both charge the low price, both earn less, since neither gains market share at the other's expense, and the lower price erodes both margins. If one firm charges low while the other charges high, the low price firm captures most of the market and earns the most of any outcome, while the high price firm earns the least. For each firm, charging low is a dominant strategy. Whatever the rival does, undercutting does better than not undercutting. Both firms reasoning this way independently land on both charging low, a Nash equilibrium, even though both would have preferred the outcome where both charged high. This is the structural reason price wars happen even when every firm involved would rather they didn't. Click any cell and the figure checks the reasoning for you. Given what the other firm chose, was this firm's choice actually its best response? Click through all 4 and notice only one cell survives that check for both firms at once, the Nash equilibrium, and it isn't the outcome either firm would have picked if they could coordinate. 8.5 Collusion and cartels. If firms could bind each other to the high price outcome instead of reasoning their way into the low price trap, every firm would be better off. A group of firms that agrees to coordinate output or price rather than compete is called a cartel. The prisoner's dilemma structure explains why cartels are inherently unstable even when every member benefits from the agreement holding, at the agreed high price. Each individual member still faces the same incentive to secretly undercut the others and capture extra market share, exactly as in the one-shot game above. A cartel survives only as long as it can detect and punish that kind of cheating, through repeated interaction, monitoring, or a credible threat of retaliation, which is precisely why cartel agreements tend to be difficult to enforce without some mechanism beyond the agreement itself. Toggle between the two assumptions. The demand curve this firm perceives isn't fixed, it depends entirely on what the firm believes its rival will do. Assume the cartel holds and the joint outcome looks stable and profitable. Assume the rival won't react to a deviation, and this firm's own optimal output jumps well past its quota, exactly the reasoning figure 8. 4's prisoner's dilemma already showed leads both firms to the worse, non-cooperative outcome. 8.6 tutorial, play the pricing game. Figure 8. 4 showed the one-shot game, where low dominates and cooperation can't survive. Play this one for several rounds against a tit-for-tat rival, and notice something different: sticking with high every round earns more, on average, than trying to defect, because unlike the one-shot game, a defection here gets punished next round. Repetition changes the incentive the static analysis couldn't capture. Chapter summary. Monopolistic competition combines free entry, like perfect competition, with product differentiation, so each firm faces its own downward-sloping demand curve, like a small monopolist. Entry drives long-run economic profit to zero, but because demand is downward-sloping, firms produce to the left of minimum average cost, the excess capacity result. Oligopoly is defined by strategic interdependence, a small number of firms, each aware that its decisions provoke a response from rivals. A dominant strategy is best regardless of the rival's choice, a Nash equilibrium is a combination where neither player can improve by changing alone. The prisoner's dilemma shows both firms can rationally reach a worse joint outcome than they could achieve by cooperating. Cartels raise every member's profit if they hold, but each member faces a private incentive to cheat, the same structure as the prisoner's dilemma, which is why cartels are hard to sustain without an enforcement mechanism. Review questions. Explain why a firm in monopolistic competition earns zero economic profit in the long run despite having some price-setting power, unlike a true monopolist. Draw, in words, why a downward-sloping demand curve tangent to a U-shaped average cost curve must touch it to the left of the cost curve's minimum, not at the minimum. Construct a payoff matrix for two firms choosing advertise or don't advertise where advertising is costly but attracts customers from a non-advertising rival. Under what payoff assumptions does advertise become a dominant strategy for both? The submarine example in section 8. 4 used a unanimity rule among 3 decision-makers. Explain, in your own words, why switching that same game to a majority rule instead, with the same 3 people holding the same preferences, could produce a different outcome, even though nothing about what anyone wanted has changed. Explain, using the prisoner's dilemma structure, why a cartel agreement made once and never revisited is more fragile than one enforced through repeated interaction. Is excess capacity in monopolistic competition a market failure in the same sense as the deadweight loss from monopoly in Chapter 7? Explain what is similar and what is different. Chapter 9, Factor Markets. Learning Objectives. Explain why the demand for labor is a derived demand, and calculate the marginal revenue product of labor. Describe the individual labor supply decision as a work-leisure trade-off, and explain why labor supply can bend backward at high wages. Find equilibrium in a competitive labor market, and explain what determines the equilibrium wage. Apply the same supply and demand logic to capital markets and the rental rate. Define economic rent, and explain why it arises specifically when a factor's supply is inelastic. 9.1 The demand for labor. Every market examined so far has asked how much of a good to produce. This chapter asks a different question: how much of an input should a firm hire? The demand for labor, capital, and other inputs is a derived demand. Firms do not want labor for its own sake, they want it because it helps produce output that can be sold. That link is what determines how much a firm is willing to pay for one more unit of an input. A profit-maximizing firm hires labor up to the point where the value of what an additional worker adds to output just equals the wage. That value is the marginal revenue product of labor, the marginal product of labor from Chapter 5's production function, multiplied by the marginal revenue from selling the extra output from Chapter 6. For a firm selling in a perfectly competitive product market, marginal revenue equals price, so the marginal revenue product of labor is just the marginal product of labor multiplied by price. The profit-maximizing hiring rule is then that the wage equals the marginal revenue product of labor, hire labor until the wage equals the value of what the last worker contributes. Because the marginal product of labor falls as more labor is added, holding capital fixed, from the same diminishing returns logic behind the short-run cost curves of Chapter 5, the marginal revenue product of labor falls with quantity of labor hired, which is exactly why the firm's labor demand curve slopes downward. For the same underlying reason any demand curve does, each additional unit is worth less than the one before it. 9.2 The supply of labor. An individual's labor supply decision is a special case of the constrained choice problem from Chapter 4, with a twist: the good being chosen is leisure, and time itself is the constraint. A person divides a fixed total number of hours between leisure and labor. Every hour worked earns a wage but gives up an hour of leisure, so the wage rate is the price of leisure. Chapter 4's income and substitution effects apply directly. A wage increase makes leisure more expensive relative to income, which by itself induces less leisure and more work, the substitution effect. But a wage increase also raises income at any given number of hours worked, and if leisure is a normal good, higher income by itself induces more leisure and less work, the income effect pulling the opposite direction. At low wages, the substitution effect typically dominates, and labor supply slopes upward as it would for an ordinary good. At high enough wages, the income effect can dominate instead. A worker who is already earning a comfortable income responds to a further wage increase by choosing to work fewer hours and enjoy more leisure, since they can now afford to. This produces a backward-bending labor supply curve, sloping upward at low wages, then bending back at high wages, the same income versus substitution tug-of-war that produced the given possibility in Chapter 4, applied here to a person's own time instead of a market good. 9.3 Labor market equilibrium. With a downward-sloping labor demand curve, section 9.1, and an individual or aggregate labor supply curve, section 9.2, a competitive labor market reaches equilibrium exactly the way Chapter 2 described for any market. The wage adjusts until the quantity of labor firms want to hire equals the quantity workers want to supply. A wage above equilibrium leaves willing workers unable to find jobs at that wage, the labor market equivalent of the surplus from Chapter 2. A wage below equilibrium leaves firms wanting to hire more workers than are willing to work at that wage, the equivalent of a shortage. Shifts in labor demand, a rise in the price of the firm's output, a change in technology that raises the marginal product of labor, or labor supply, population growth, a change in preferences for leisure, move the equilibrium wage and quantity exactly as the corresponding shifts did for an ordinary good in Chapter 2. The labor market from sections 9.1.9. 3 is the same supply and demand model as Chapter 2, with the axes relabeled quantity of labor instead of quantity of a good, and the wage instead of price. Firms are the buyers, so the red region is their surplus, workers are the sellers, so the blue region is theirs. Drag the yellow wage line away from equilibrium to see the surplus and shortage story from section 9.3 play out directly. Pull the wage up and a purple bar marks the resulting unemployment. More workers want jobs than firms want to hire. Pull it down and an orange bar marks the resulting shortage. Firms want to hire more than are willing to work. Either way, only the smaller quantity is actually hired, and the gray triangle marks the resulting deadweight loss. jobs that would have benefited both a firm and a worker but no longer happen. 9. For monopsony, when the buyer has power. Section 9. 3s. Equilibrium assumed a competitive labor market, many employers, none large enough to affect the wage by hiring more or fewer workers, each simply reading the going wage of the market and deciding how much labor to demand at it. That assumption is doing exactly the same work Chapter 6 made explicit for firms selling output. It is the buying side mirror of price taking, and just as worth naming rather than leaving silent. A monopsony is a market with a single buyer, here, a single employer, perhaps the only significant one in a small town. Because it is the only buyer, the labor supply curve it faces is not a fixed wage, but the entire upward-sloping market supply curve. To hire one more worker, it must raise the wage, and, critically, it must raise that wage for every worker it already employs, not just the new one. The cost of hiring one more worker, the marginal factor cost, MFC, therefore exceeds the wage itself, by exactly the extra amount paid to everyone already on the payroll. For a linear supply curve, this produces the identical geometric relationship Chapter 6 derived for revenue. MFC lies above supply, and rises, at twice the rate, the same twice the slope result, as marginal revenue below average revenue, just flipped from the selling side of a market to the buying side. A profit-maximizing monopsonist hires up to the point where marginal factor cost equals the value of an extra worker's output, the marginal revenue product of labor, the same logic as any profit-maximizing hiring decision, just facing marginal factor cost instead of the wage. Because marginal factor cost lies above supply, the monopsonist's hiring stops short of the competitive quantity, and the wage it pays, read off the supply curve, not the marginal factor cost curve, since supply is what determines what workers must actually be paid to be willing to work, sits below both the competitive wage and below the marginal revenue product of labor itself. Workers are paid less than the value of what they produce, not because the firm is acting unfairly in any individual transaction, but because it is exploiting the same kind of market power a monopolist exploits when selling, a markdown, mirroring the monopolist's markup. Drag the yellow minimum wage line. Below the unregulated monopsony wage it does nothing. Between the monopsony wage and the competitive wage, watch employment rise as the minimum wage rises. The firm is being forced to stop underpaying, not being taxed out of hiring. Only once the minimum wage climbs above the competitive wage does the ordinary Section 2.5 result take over and employment starts to fall. The bottom panel traces the whole relationship, a hump, not a straight line, peaking exactly at the competitive wage. This is why the employment effect of a minimum wage is an empirical question, not something the theory alone can settle in advance. A modest minimum wage can raise employment in a market with real monopsony power, and reduce it in a genuinely competitive one, and the same policy can do either depending on which kind of market it lands in. Real labor market studies, most famously Card and Kruger's comparison of neighboring fast food markets after a minimum wage increase, and the broader empirical literature on employer wage setting power that followed it, are, in effect, attempts to find out how much monopsony power actually exists in the markets being regulated. 9.5 Capital markets, and the rental rate. The same apparatus applies to capital. Firms demand capital up to the point where its marginal revenue product equals the rental rate R, the price of using a unit of capital for a period, whether that capital is rented from someone else or represents the opportunity cost of capital the firm already owns. The supply of capital comes from savers willing to forego present consumption in exchange for a return. A higher rental rate makes saving, and hence supplying capital, more attractive, so capital supply typically slopes upward without the backward bending complication labor supply has, since capital does not carry the same built-in leisure alternative a worker's own time does. Equilibrium in the capital market determines R exactly as equilibrium in the labor market determines W, and together, W and R are the same factor prices that have quietly driven every isocost line since Chapter 5. 9.6 Economic Rent. Economic rent is any payment to a factor of production above the minimum amount required to bring that factor into use, its opportunity cost. Most factors earn some combination of a required minimum payment plus a rent on top of it. The concept is clearest at the extreme where a factor's supply is completely fixed regardless of price, a plot of land in a unique location, for instance. Because supply does not respond to price at all, the entire payment for such a factor is economic rent. The factor would be supplied at any positive price, so every dollar paid above zero is a rent rather than a payment needed to call the factor into existence. More generally, the more inelastic a factor's supply, the larger the share of its payment that is economic rent rather than a price needed to secure its use. Drag left or right to change how elastic this factor's supply is, holding the price and quantity actually paid fixed. The blue region is opportunity cost, what the factor would need to be paid, at minimum, to bring each unit into use. The orange region above it is economic rent, pure surplus collected simply because the market price is what it is. The same picture applies to labor, sections 9193, capital, section 95, or land. The more inelastic the supply, the larger the rent share, exactly as the text describes. 9.7 Tutorial, Shift a labor market. Drag either slider. A demand shock might be a change in technology or the price of the firm's output, section 9.1. A supply shock might be immigration or a change in preferences for leisure, section 9.2. This is the same competitive labor market from section 9.3, a different market from figure 9. 2's monopsony case, which fixes the wage below competitive levels through a single buyer's power rather than shifting the whole market. Chapter Summary. Labor demand is a derived demand. Firms hire up to the point where the wage equals the marginal revenue product of labor, the marginal product of labor multiplied by marginal revenue. Individual labor supply is a work-leisure trade-off. Income and substitution effects from Chapter 4 can produce a backward-bending supply curve at high wages. Competitive labor markets reach equilibrium the same way any market does. The wage adjusts until quantity demanded equals quantity supplied. A monopsonist, a single buyer of labor, faces the entire upward-sloping supply curve, so hiring one more worker raises the wage paid to everyone already employed. Marginal factor cost lies above supply, and rises at twice the rate. The same geometric relationship as Mr. below are from Chapter 6, mirrored to the buying side. This pushes wages and employment below the competitive level. A minimum wage between the monopsony and competitive wage raises employment. Only above the competitive wage does it reduce employment as usual. Capital markets work the same way, with the rental rate are playing the role the wage plays for labor. Economic rent is payment above a factor's opportunity cost. It makes up a larger share of payment the more inelastic the factor's supply is, and all of it when supply is perfectly inelastic. Review questions. A firm's marginal product of labor at its current hiring level is 5 units, and it sells its output at $10 per unit in a competitive product market. What is the most this firm should be willing to pay in wages to hire one more worker? Explain, using income and substitution effects, why a lottery winner might choose to work fewer hours even though their hourly wage has not changed. Why does the marginal revenue product of labor use Mr. rather than price for a firm with monopoly power in its product market, and how would that change the firm's labor demand curve compared to a competitive firm with the same production technology? Explain why a professional athlete with a unique, irreplaceable skill earns an income that is mostly economic rent, while a worker in a job requiring easily learned skills earns very little rent. Sketch, in words, what happens to the equilibrium wage and employment level in a labor market if immigration increases labor supply at every wage, holding labor demand fixed? A monopsony employer pays a wage below the marginal revenue product of labor. Explain why a modest minimum wage set above the monopsony wage but below the competitive wage increases employment rather than reducing it, and explain precisely what changes once the minimum wage is raised past the competitive wage instead. Chapter 10, Market Failure and Externalities. Learning Objectives. Distinguish private cost and benefit from social cost and benefit, and explain how a negative or positive externality drives a wedge between them. State the Coase theorem and explain the conditions under which private bargaining resolves an externality without government intervention. Distinguish public goods from private goods and ordinary common resources, using excludability and rivalry. Explain the free rider problem and the tragedy of the commons as two sides of the same excludability and rivalry structure. Describe the main policy responses to market failure and explain what each is designed to correct. 10.1 Externalities, positive and negative. Every market examined so far reached an efficient outcome precisely because the price paid by buyers and received by sellers reflected the full cost and benefit of the transaction to them. An externality is a cost or benefit of a transaction that falls on someone who is not a party to it. A factory that pollutes a river imposes a cost on people downstream who were never part of the sale between the factory and its customers, a negative externality. A homeowner who plants a garden that beautifies the whole street, or a person who gets vaccinated and thereby reduces disease transmission to others, creates a benefit that people outside the transaction receive for free, a positive externality. The key distinction driving everything else in this chapter is between private cost or benefit, what the buyer and seller actually weigh when deciding on a transaction, and social cost or benefit, the full cost or benefit to everyone affected, including bystanders. With a negative externality, social cost exceeds private cost, so a market left alone produces more than the efficient quantity. The transacting parties do not pay for the harm they impose on others, so they keep transacting past the point where total costs exceed total benefits. With a positive externality, social benefit exceeds private benefit, so a market left alone produces less than the efficient quantity. The parties do not capture the benefit that spills over to others, so they stop transacting before that point. Press play with narration to watch the reveal. The market first as it looks with nothing accounted for, then the true social cost or benefit emerging and the deadweight loss opening up with it. Notice the triangles are identical in size, just pointing opposite directions. One is the cost of too much happening, the other the cost of too little. Figure 10. 4's tutorial shows the tax fix for the negative case in detail. A positive externality calls for the mirror image tool, a subsidy, closing the same kind of gap from the other side. 10.2 The Coase theorem. The Coase theorem makes a striking claim: if property rights are clearly defined and the parties can bargain with each other at negligible cost, private negotiation will resolve an externality efficiently regardless of which party initially holds the rights. If a factory has the legal right to pollute, downstream residents harmed by the pollution have an incentive to pay the factory to reduce it, up to the value of the harm avoided. If residents have the right to a clean river instead, the factory has an incentive to pay residents for permission to pollute, up to the value of the output that pollution enables. Either way, bargaining pushes the outcome toward the efficient quantity of pollution, the point where the marginal cost of reducing it further exceeds the marginal benefit of doing so. The theorem's real content is in its conditions, not its conclusion. Well-defined property rights and low transaction costs are doing all the work. When many people are affected, when it is difficult to identify who is imposing costs on whom, or when negotiating and enforcing an agreement is itself costly, private bargaining breaks down and the efficient outcome from the theorem does not arise on its own. This is precisely why externalities remain a live policy problem rather than something markets quietly solve themselves. The Coase theorem identifies the conditions under which government intervention is unnecessary, which is also a map of exactly where those conditions tend to fail. 10.3 Public goods. Goods can be classified along two dimensions, whether one person's use prevents another's, rivalry, and whether people who do not pay can be prevented from using the good anyway, excludability. An ordinary private good, a sandwich, is both rival and excludable. A public good is non-rival, one person enjoying it does not reduce how much is available to anyone else, and non-excludable, no one can be stopped from benefiting once it exists. National defense and a public fireworks display are standard examples. Because no one can be excluded, no one has a private incentive to pay for a public good voluntarily, each person would rather let others pay, and enjoy the benefit anyway. This is the free rider problem, and it is why public goods tend to be underprovided by private markets even when their total social benefit far exceeds their cost, the same underprovision logic as a positive externality, in the extreme case where the spillover to others is total. If the free rider problem could somehow be solved, if everyone reported their true willingness to pay rather than trying to ride free, there is still a real question of how to find the efficient quantity to provide, and how to split the cost. Lindell pricing answers both at once, using a mechanism that looks like Chapter 2's market demand, but works in the opposite direction. For an ordinary private good, market demand sums individual demand curves horizontally, at a given price, add up how much quantity each person wants, since each person can buy a different amount. A public good doesn't allow that, everyone necessarily consumes the same quantity, since one person's use doesn't reduce what's available to anyone else. So the meaningful sum is vertical instead, at a given quantity, add up how much each person would be willing to pay for it, since what matters is their combined valuation of that same unit. The efficient quantity is where this vertically summed willingness to pay curve crosses marginal cost, and each person's Lindell price is simply their own individual willingness to pay at that quantity, which will generally differ from person to person even though everyone receives the identical quantity of the good. Drag the quantity line away from Q*, notice the stacked price bar's total either exceeds or falls short of the orange MC line \U 2014 telling you which direction improves efficiency. Only at Q*, does the combined willingness to pay land exactly on MC, and it's the only quantity where neither person would want more or less provided. Lindell pricing is elegant in theory, but runs straight back into the free rider problem in practice. Finding each person's Lindell price requires knowing their true willingness to pay, and the same incentive to understate that value in order to pay less applies here exactly as it does to voluntary contribution. It is a benchmark for what an efficient outcome would look like, not a mechanism anyone can straightforwardly run, which is precisely why real public goods are typically funded through general taxation instead, sidestepping the elicitation problem entirely rather than solving it. 10.4 Common resources. A common resource occupies the opposite corner of the same grid. It is rival. One person's use does reduce what is left for others, but non-excludable. No one can be stopped from using it. An open ocean fishery or an unregulated grazing pasture are standard examples. Because no individual user bears the full cost of their own use, some of that cost falls on everyone else who shares the resource, exactly the negative externality structure of Section 10. 1. Each user has an incentive to use more of the resource than the socially efficient amount, and the resource gets overused or depleted. This is the tragedy of the commons, individually rational decisions by each user, in the absence of any mechanism to make each user account for the cost imposed on the others, produce a collectively worse outcome than coordinated use would. The logic can be made precise. As more herders bring animals to the same pasture, the average value per herder falls. There is only so much grass, split more ways. But the true marginal value that one more herder adds to total output falls twice as fast. For the same reason marginal revenue fell twice as fast as average revenue in Chapter 6. Each new herder's animals don't just produce their own output, they also reduce what every existing herder's animals can find to eat. A prospective herder compares only the average value they personally expect to earn against what they could earn doing something else, never the damage their entry does to everyone already there. Herders keep entering as long as the average payoff beats the outside alternative, which pulls the pasture well past the point where an additional herder's true contribution to total value has fallen to zero, or even negative. Drag the orange line to change how many herders use the pasture. The efficient number stops where the true marginal value line crosses the outside opportunity line. Open access keeps pulling herders in until the average value line crosses it instead, always further out, since average value stays above marginal value throughout. The gray triangle between them is the resulting welfare loss, value that a herder's next best alternative would have created, given up for animals whose marginal contribution to the pasture is now worth less than that. 10.5 Government responses to market failure. Several policy tools target these problems directly. A Pigouvian tax on a good with a negative externality, set equal to the external cost per unit, makes the private cost faced by the transacting parties equal to the true social cost, restoring the efficient quantity without needing to identify or negotiate with every affected bystander individually. A Pigouvian subsidy does the same for a positive externality, closing the gap between private and social benefit. Cap and trade systems set a total quantity limit and let a market in permits find the efficient allocation of who reduces how much, combining a quantity restriction with the price discovery Chapter 2 already relies on. For public goods, direct government provision funded by general taxation sidesteps the free rider problem by removing the option not to pay. For common resources, defining and enforcing property rights, converting a non-excludable resource into an excludable one, restoring the conditions the Coase theorem requires, is one standard remedy, direct regulation of quantities used is another. 10.6 Tutorial, correct a market failure yourself. Drag the orange tax marker. Too little tax and the market still overproduces past the efficient point, too much and it underproduces instead. Only one tax level makes the deadweight loss vanish entirely, and it isn't a coincidence that it's exactly equal to the external cost per unit, which is precisely section 10. 5's Pigouvian principle. Chapter summary. An externality is a cost or benefit falling on someone outside a transaction. Negative externalities cause overproduction relative to the efficient quantity, positive externalities cause underproduction. The Coase theorem says private bargaining resolves externalities efficiently when property rights are well defined and transaction costs are low, conditions that identify exactly where the theorem tends not to apply. Public goods are non-rival and non-excludable, creating a free rider problem that leads private markets to underprovide them. Common resources are rival but non-excludable, creating the tragedy of the commons, overuse because no individual user bears the full cost of their own use. Pigouvian taxes and subsidies, cap and trade, direct provision, and property rights assignment are the standard policy responses, each targeting a specific gap between private and social incentives. Review questions. Explain, in terms of private versus social cost, why an unregulated market with a negative externality produces more than the efficient quantity rather than less. A factory and a downstream fishery could bargain over a pollution-reducing filter that costs less than the value of the fish it would save. Explain 2 realistic reasons this bargain might not happen even though the Coase theorem says it should. Classify each of the following by rivalry and excludability, and name the resulting category: a toll road with electronic payment, a public park with no entry fee, an overfished open access lake. Explain why a Pigouvian tax set exactly equal to the external cost per unit restores the efficient quantity, using the private cost versus social cost framework from section 10. 1. Why does converting a common resource into a set of enforceable private property rights tend to reduce the tragedy of the commons problem, even without any change in how much anyone values the resource? Chapter 11, The Production Possibilities, Frontier and Trade. Learning Objectives. Read a production possibilities frontier, and explain why it is typically bowed outward. Calculate opportunity cost, and determine which of two producers holds the comparative advantage in a good. Explain, using a diagram, how trade at a shared world price lets both producers consume beyond their own individual frontier. 11.1 The production possibilities frontier. The trade-offs created by scarcity can be shown visually with a production possibilities frontier. Production possibilities frontier, a curve showing the maximum combinations of two goods an economy can produce given its resources and technology, when those resources are fully and efficiently employed. Points inside the frontier are achievable but wasteful, some resources are idle or mislocated. Points outside the frontier are simply not achievable with current resources and technology. Points on the frontier itself represent full, efficient use of everything the economy has to work with. The standard production possibilities frontier is drawn bowed outward from the origin, and this shape is not arbitrary, it reflects the economic principle of increasing opportunity cost. Resources are not equally well suited to producing every good. As an economy shifts more and more resources toward one good, it must eventually redirect resources that were comparatively better suited to producing the other good, so each additional unit of the first good costs progressively more units of the second. The bowed-out shape is the graphical signature of that principle. Figure 11. 1 shows the frontier for an economy producing just two goods, food and machinery, so the whole trade-off fits on a page. Every point on the blue curve represents full, efficient use of the economy's resources. Points A and B are two such points, one favoring food, the other favoring machinery. The shaded region beneath the curve is achievable but wasteful, and the region above it is simply not achievable with current resources and technology. Drag the orange point along the curve, the readout beneath it recalculates the opportunity cost at that exact spot, how much machinery one more unit of food actually costs there. Notice that this cost is not constant. It rises the further the economy pushes toward one good, which is exactly the increasing opportunity cost principle from the previous page, made tangible rather than just asserted. 11.2 Producers, comparative advantage. The producer behind figure 11. 1 is not the only one who can grow food or build machinery. Trade only becomes interesting once a second producer enters the picture. Suppose a neighboring producer, call it abroad, has its own resources and technology, and its own trade-off between the same two goods. Comparing the two producers' opportunity costs, rather than their raw output totals, is what determines comparative advantage. Whichever producer gives up less of one good to get a unit of the other holds the comparative advantage in that good, regardless of which producer is simply bigger or more productive overall. Real production trade-offs are rarely straight lines. Section 11. 1 already established that a production possibilities frontier is normally bowed outward. Figure 11. 2 draws both producers' bowed frontiers on the same axis. Home's curve bulges further out along the food axis, abroad's curve bulges further out along the machinery axis, and the two curves cross, exactly the picture textbooks use when two producers have different comparative advantages. With only two producers, and nothing outside the system, there can be exactly one world price line. Whatever home sells, abroad must buy, and whatever abroad sells, home must buy, so both producers have to face the same trade-off between the two goods. Press replay to watch the proof. Each producer starts at some Ortiki bundle on its own curve. Then a single price line appears, positioned so it is tangent to home's curve at one point and, without moving or changing slope at all, also exactly tangent to abroad's curve at a different point. That is not a coincidence built into the drawing, it is the one line whose slope and positions solve both tangency conditions simultaneously, and it is the graphical meaning of a market that clears. Each producer then slides along that same shared line to a new consumption bundle, one paying out some of what it produced, the other receiving it, in exactly matching amounts, and both bundles end up strictly outside the producer's own frontier. Neither home nor abroad could have produced what it now consumes, working alone. Note what this comparison does not depend on, which producer is bigger, or which one could outproduce the other at everything. Comparative advantage is about the trade-off each producer faces internally, not about the scale of what either one can do. If home specializes toward food, and abroad specializes toward machinery, then trades, both producers can end up with more of both goods than either could have produced alone. The mechanics of exactly how much more belong to a later chapter on trade, but the underlying reason is already fully visible in the opportunity cost numbers above. 11.3 Tutorial, Comparative Advantage and Trade. Figure 11. Two used bowed frontiers, which is the realistic case, but bowed curves make the arithmetic of opportunity cost change at every point along them. To let you experiment freely, the tool below simplifies each producer back down to a straight line production possibilities frontier, a constant opportunity cost everywhere along the curve, so that changing a slider has one clean, calculable effect. Set each producer's maximum output yourself and see, instantly, who ends up with a comparative advantage in which good. Try pushing home's maximum machinery down toward its maximum food. As the two numbers converge, watch the opportunity costs converge too, and notice what the status line says once they are equal: no comparative advantage, and nothing to gain from trade. Comparative advantage disappears not when a producer becomes weak, but when the two producers' internal trade-offs happen to match. Chapter Summary. The production possibilities frontier shows the maximum combinations of goods an economy can produce with full, efficient use of its resources. It is bowed outward because of increasing opportunity cost. Comparative advantage belongs to whichever producer has the lower opportunity cost of a good, regardless of which producer is larger or more productive overall. It is the basis for mutually beneficial trade. In a closed system of two producers, there is exactly one world price line, tangent to both producers' frontiers at once. Trading along it lets both producers consume bundles their own frontier alone could never reach. Review questions. Why is a point outside the production possibilities frontier not simply very efficient but actually unachievable? Explain in your own words why the production possibilities frontier is bowed outward rather than a straight line, using the idea that resources are not equally suited to every use. Producer X can make 8 units of cloth or 4 units of wine. Producer Y can make 8 units of cloth or 8 units of wine. Which producer has the comparative advantage in wine? Which in cloth? Show your opportunity cost calculation for each. Look back at Chapter 5 SI sequence. Explain, in your own words, why resources are not equally productive in every use turns out to be the same underlying idea driving both a firm's cost curves and a whole economy's production possibilities frontier. Chapter 12, General Equilibrium and Exchange. Learning Objectives. Explain what an Edgeworth box represents and how it displays two consumers' allocations of two goods simultaneously. Find the contract curve and explain why every point on it, and only points on it, is Pareto efficient. Explain how competitive trading from an initial endowment leads to a single world price and an allocation on the contract curve. Explain how an analogous Edgeworth production box generates the production possibilities frontier from Chapter 11. State the connection between competitive equilibrium and Pareto efficiency that this chapter's construction demonstrates. 12.1 The Edgeworth box, endowments and trade. Every previous chapter analyzed one market at a time, holding everything else fixed. This final chapter puts two goods and two people in the same picture at once, to ask a question none of the earlier apparatus could. Starting from whatever goods people happen to have, does trading between them lead anywhere in particular, and is that destination any good? An Edgeworth box answers this for the simplest possible case: two consumers, call them A and B, and two goods, X and Y. The box's width is the total quantity of X available between them, its height is the total quantity of Y. A point inside the box represents a complete allocation. A's consumption is measured from the bottom left corner, and by construction whatever A does not have, B has, measured from the top right corner running the opposite way. The endowment point marks what each person starts with, before any trading happens. This is the same starting bundle Chapter 4's budget line took as given, except now both sides of the exchange are inside the same diagram, so what one person gains, the other must give up. Draw each consumer's indifference curves from Chapter 4 inside the box, A's running the usual way from A's corner, B's running the mirror image way from B's corner. Wherever the two consumers' indifference curves cross at the endowment point rather than sit tangent to each other, both curves have a region between them where both consumers would be better off than at the endowment. A trade exists that both parties would voluntarily agree to. Drag anywhere in the box, and watch both consumers' indifference curves redraw through wherever you land. Most points make the curves cross. A trade exists there that would help both parties. Hunt for a point where they touch instead of cross, that's section 12. 2's Pareto efficiency condition, and the grey dashed curve traces every such point. This one figure carries sections 12. 1 through 12. 3. Revisit it as each section builds on what it already shows. 12.2 The contract curve and Pareto efficiency. An allocation is Pareto efficient if no other allocation could make one person better off without making the other person worse off. Inside the Edgeworth box, that condition has a precise geometric meaning. An allocation is Pareto efficient exactly where A's and B's indifference curves are tangent to each other, so that A's marginal rate of substitution equals B's. At any point where the curves cross instead of touching tangentially, a trade exists that helps one party without hurting the other, exactly the gap section 12. 1 identified, so a crossing point cannot be efficient. The locus of every tangency point, running from A's corner of the box to B's, is called the contract curve. Every point on it is Pareto efficient, and every Pareto efficient allocation of the two goods between the two people lies on it. The contract curve does not pick out a single best allocation, it contains many points, ranging from ones that favor A heavily to ones that favor B heavily, and all of them are equally Pareto efficient by this definition. Pareto efficiency is a statement about whether any remaining mutually beneficial trades exist, not a statement about fairness. A contract curve point that gives A almost everything and B almost nothing is just as Pareto efficient as one that splits the goods evenly, since moving away from either would require making someone worse off. 12.3 Deriving the world price. Section 12. 1. Established that trade happens whenever the endowment point is not already on the contract curve. But which point on the contract curve does trading actually reach? A competitive market answers this the same way Chapter 2 did for a single good. A price ratio between X and Y defines a budget line through the endowment point. The same price ratio slope from Chapter 4's budget constraint, and each consumer chooses their utility maximizing bundle along that line, exactly as in Chapter 4. Because the budget line runs through the same endowment point for both consumers by construction, whatever A buys, B must be selling, and vice versa, trade between them is automatically balanced at every price ratio. Equilibrium requires more than balance, though. It requires that A's desired trade and B's desired trade at the given price actually match up, good for good. At most price ratios they will not. A wants to buy more X than B wants to sell, say, and that imbalance is exactly the excess demand Chapter 2 used to find a single market equilibrium price. The world price is the one price ratio at which both markets, for X and for Y simultaneously, clear at once. The quantity of X one consumer wants to buy exactly equals the quantity the other wants to sell, and the same holds for Y. At that price, both consumers' chosen bundles coincide at a single point. which turns out to be a point of mutual tangency, a point on the contract curve. Competitive trade from an arbitrary endowment therefore reaches a Pareto-efficient allocation without either consumer aiming for efficiency directly, each is simply maximizing their own utility from Chapter 4, taking the price as given. 12 For the Edgeworth production box and the origin of the production possibilities frontier. The same box construction applies to production instead of consumption. Put two firms in a box whose dimensions are the economy's total labor and total capital. Draw each firm's I-sequence from Chapter 5, one running the usual way, one mirrored, exactly as the consumer's indifference curves were, and the same tangency logic applies, an allocation of labor and capital between the two. Firms is production efficient only where their I-sequence are tangent, where both firms' marginal rates of technical substitution are equal. The locus of these tangencies is the production analog of the contract curve. Each tangency point corresponds to a specific pair of output quantities, so much of good X, so much of good Y, produced efficiently given the economy's total labor and capital. Plotting every tangency point's output pair in quantity of X, quantity of Y space traces out exactly the production possibilities frontier from Chapter 11, not asserted as a smooth bowed-out curve the way it was first introduced, but derived from the same tangency condition that generated the consumption-side contract curve in Section 12. 2. The production possibilities frontier's bowed-out shape is the production box's contract curve, viewed in output space instead of input space. 12.5 General equilibrium, production and exchange together. The full picture links both boxes together. Firms choose a point on the production side contract curve, equivalently, a point on the production possibilities frontier, guided by relative prices exactly as Chapter 11 described, since the slope of the production possibilities frontier at any point is the opportunity cost ratio, and profit maximizing firms produce where that ratio matches the relative price of the two goods. That output split then becomes the total endowment available to distribute between consumers in the consumption side Edgeworth box from sections 12. 1 through 12. 3. Where the world price from section 12. 3 determines how it actually gets divided. When a single set of prices simultaneously clears the market for every good and every input, so firms are choosing efficient production, consumers are choosing efficient trades, and every plan is mutually consistent, the economy is in general equilibrium. The result this whole chapter has been building toward, known as the first welfare theorem, is that a competitive general equilibrium is Pareto efficient in both production and exchange simultaneously, no reallocation of inputs between firms, or of goods between consumers, could make anyone better off without making someone else worse off. Every earlier chapters separate marginal revenue equals marginal cost and marginal rate of substitution equals price ratio conditions, derived market by market, turn out to be exactly the conditions this single, economy-wide tangency requires. 12.6 Tutorial, explore the Edgeworth box yourself. A figure for this section, a draggable Edgeworth box with two sets of indifference curves, the contract curve traced live, and a price line tool for finding the world price from section 12. 3. Is not yet built. This section is a placeholder for it. Chapter Summary. An Edgeworth box displays a complete allocation of two goods between two consumers at once, the endowment point is where they start before trading. An allocation is Pareto efficient exactly where the two consumers' indifference curves are tangent, the locus of all such tangencies is the contract curve. Competitive trade at the world price, the price ratio that clears both goods markets simultaneously, moves consumers from the endowment point to a point on the contract curve, without either consumer aiming at efficiency directly. The same tangency logic applied to two firms' I-sequence over the economy's total labor and capital traces out the production possibilities frontier from Chapter 11. The first welfare theorem, a competitive general equilibrium, linking efficient production to efficient exchange through a single set of prices, is Pareto efficient overall. Review questions. Explain why a point where two consumers' indifference curves cross, rather than touch tangentially, cannot be Pareto efficient. Two allocations both lie on the contract curve, but one gives consumer a far more of both goods than the other does. Are both still Pareto efficient? Explain why Pareto efficiency does not resolve which of the two is preferable. Explain, in your own words, why a competitive price ratio that fails to clear the market for good X must also fail to clear the market for good Y, given a fixed total endowment of both goods between two consumers. Explain how the Edgeworth production box's contract curve, plotted in output space, becomes the bowed-out production possibilities frontier from Chapter 11 rather than a straight line. The first welfare theorem shows competitive equilibrium is Pareto efficient. Explain why this is a narrower claim than competitive equilibrium is fair or competitive equilibrium is the best possible outcome using the contract curve discussion from section 12. 2. Appendix, Modeling Notes. Every figure in this book is exact within the terms it sets for itself, given its stated assumptions. The curves, tangences, and equilibria it draws are genuinely computed, not sketched to look plausible. But those stated assumptions are themselves simplifications of a much messier reality, chosen deliberately for pedagogical reasons, clarity, calculability, or consistency with a figure elsewhere in the book. This appendix collects the most consequential of those choices in one place, rather than leaving them scattered across individual captions and code comments, so a reader can see at a glance where the book is being exact and where it is being illustrative. A one where the curves are drawn straight. Market demand and supply curves are drawn as straight lines throughout chapters 2 and 3. This is the standard introductory convention, not an empirical claim. A straight-line demand curve has a finite maximum price, where it meets the vertical axis, and therefore a finite, calculable consumer surplus, the figures in section 2. 1 and 2. 3 note this explicitly. Real demand and supply relationships are typically curved, and the choice trades that realism for arithmetic a reader can follow by hand. The same trade-off appears in Chapter 11's Comparative Advantage Tool, Figure 11. 3, which simplifies each producer down to a straight-line production possibilities frontier, a constant opportunity cost at every point along the curve, so that moving a slider has one clean, calculable effect on who holds the comparative advantage. Section 11. 1's own production possibilities frontier figure draws the more realistic bowed-out case, and discusses why opportunity cost normally rises as a producer specializes further. The straight-line version is confined to the interactive tool, where the point is letting a reader experiment freely rather than deriving the general shape. A 2y Cobb-Douglas, and where it runs out. The Cobb-Douglas functional form, shown below for both utility and production, is used throughout the book as the standard teaching example, in Chapter 4's Utility Surface, Chapter 5's isequant map, and Chapter 12's Edgeworth box. Its geometry is fully general in the sense that matters for those figures, the tangency conditions, indifference curves, and isequants it produces are genuine, well-behaved examples of the broader theory, not special cases that happen to look right. 2 places in the book flag where Cobb-Douglas's specific predictions stop being general results and become artifacts of the functional form itself. The long-run average cost curve, Chapter 5, Section 5.2. A genuine U-shaped long-run average cost curve cannot be derived from a single Cobb-Douglas production function, that requires either a fixed short-run factor, introduced in Section 5.5, or a richer technology than constant elasticity Cobb-Douglas admits. The cost curves shown alongside the fully general isequant map therefore use representative numbers chosen to produce the U-shape most textbooks draw, rather than being algebraically derived from the surface above them. The text flags this directly as a simplification worth remembering, not forgetting. The Giffen good, Chapter 4, Figure 4.3. Cobb-Douglas preferences can never generate genuine Giffen behavior. Their income and substitution effects always move in the same direction by mathematical construction, so a price fall can never reduce quantity demanded. Figure 4. 3 therefore uses a schematic, not formula-derived, decomposition, chosen and verified by hand to satisfy the arithmetic of the Slutsky decomposition from section 4. 5, rather than an output of the book's usual utility function. The figure's own code comments and the surrounding prose both disclose this. Elsewhere, Cobb-Douglas's more specific predictions are flagged as specific rather than general when they arise. Chapter 5 notes that a straight-line expansion path through the origin is a distinctive prediction of Cobb-Douglas technology, not a general law of production, and Chapter 12's Edgeworth box, Section 12. 1. Deliberately gives the two consumers asymmetric preference weights, since identical Cobb-Douglas preferences would make the contract curve degenerate into the box's diagonal, a correct but illuminating special case. A 3 numbers chosen for the picture, not derived from it. A number of figures use round, hand-picked numbers rather than deriving every value from a single underlying model. The market baseline first introduced in Chapter 2, a linear demand curve, and the cost technology behind supply, giving an equilibrium quantity of 6 and a minimum price of 2. 4, recurs across Chapters 2, 3, 5, 6, and 7 deliberately, so that a reader who has internalized one chapter's numbers recognizes them again rather than relearning a new market each time. Chapter 10's Externality Figures, Section 10.1, Section 10. 6. Similarly use a round external cost of 3, chosen so that the efficiency restoring Pigouvian tax lands on a clean, exactly locatable value rather than an arbitrary decimal. These choices trade a small amount of realism. Real markets rarely have such tidy numbers. For a bigger pedagogical payoff, a reader can verify the arithmetic themselves, and recognize the same market reappearing as new concepts are layered onto it. A 4 figures held deliberately distinct. A few figures that could plausibly have been merged were kept separate on purpose, so that each one demonstrates a single idea clearly rather than several ideas at once. Chapter 10's Externality Reveal, Figure 10. 1. Animates only the gap opening up between private and social cost or benefit. The correction, a Pigouvian tax closing that gap, is left entirely to Figure 10. 4's own tutorial, rather than duplicated across both. The two figures are designed to be read together, but neither tries to do the other's job. None of the simplifications listed in this appendix affect the book's core results. Every tangency condition, every equilibrium, and every welfare comparison in the text is derived honestly from the model as stated. What varies from figure to figure is how much of the underlying model is fully general versus chosen for a specific, disclosed pedagogical reason, and this appendix is intended as a single place to check which is which.